Hi, everyone. So let's get started. First of all, welcome to week 2, day 2 of BCI 101. Thank you for being here and a really warm welcome. We've got a fantastic event for you today. We're going to be looking at how to start your experiment. We've got some fantastic speakers as well. So we have Lauren Brant from OpenVIBE in France, Yuri Nusdin from Resonance in the Netherlands, and Robin Schermeister from Germany from BrainDecode. So some fantastic speakers coming up for you. Do stay tuned and we will have lots of opportunities for question and answers as well afterwards. But first, what I want to do is just provide you guys with a little bit of information about NeurotechX and these events, just to let you know a little bit about what we're doing behind the scenes at NeurotechX. So I've just popped a presentation up on the screen. Hopefully you guys can see that okay. This is our BCI 101 Global Event Series. Sorry, just lost my signal there. So I'm having a bit of trouble sharing my screen, guys. So I think I'm going to give you a vocal presentation of what this is all about. And I'll see if I can get the slides working in the meantime. So NeurotechX, who are we? We are the global community for neurotech enthusiasts. If you haven't come across us before, welcome. We're really pleased to have you join our event. We are an international community, and what we do is we facilitate the advancement of neurotechnology in all of the different ways we can. So our 3 pillars are community. We like to bring people together, build communities where people are encouraged to bring forward ideas and to make connections and even to start companies. We also work with education. We love to educate our communities, and that's what this event is all about. We have loads of resources online, so do check out our information. You can find us at neurotechx.com. We're also all about innovation. We want to inspire and support the next generation of all of the really cool stuff, the life-changing stuff, the medical applications, the turn on your lights just thinking about it kind of stuff. That's what we're all about. We have a few different initiatives. We have chapters. I think we have about 20 chapters all over the globe. Do find your local chapter if you're not already a member of one of them. We have lots of student clubs if you're just getting started in the world of neurotech from lots of fantastic universities. And a big pillar is our Slack community. You'll find information about how to join that in the chat as well. As mentioned, we've got also our education platform and a newsletter that we send around once a month with all of the fun developments that have been happening in the world of neurotech, and also job opportunities as well, which leads us on to one of our final initiatives, which is NTX services. So if anyone out there is looking to recruit someone, or they're looking for a job themselves, or they're looking for consulting, do get in touch with us. We'd be really happy to help you, and we've got some fantastic people on board who can support on those initiatives. And do join the conversation, join us on Slack. As mentioned, the link is in the chat there. We've got about 4,000 members, just over. So, whoever you're looking to speak to, they're probably definitely in there. And there are some great people to share conversations with and to kind of really inspire your next neurotech project or the next exciting thing that you want to hear about. For this event in particular, it's the BCI 101 channel that you want to hop into, and that's where the chat's really popping off. Don't forget to stay up to date with us. So you'll find us on Twitter at NeurotechX, and the London chapter as well at Neurotech London. So this event is actually a collaboration between the Moscow chapter at Neurotech MSK and the London chapter as well. You'll also find our events on Meetup, and you can also pop us an email. All of this information is available on our website, and we would love for you guys to get in touch. This event it's partially between NeurotechX, and it's also sponsored by the Center for Neurobiology and Brain Restoration and Skulltech. So massive thank you to our sponsors there. So do stay in touch, everyone. And what I think I might do is pass over to our first speaker, who is Lauren Brant. Lauren, can you hear me okay? Would you be happy to take control of the reins?
Whatever you are on the earth, I'm very happy to join you in this community. Can you hear me very well?
Yeah, we've got you, Lauren. And if you want to present your screen as well, if you've got anything you want to share with us, that would be, yes, there we go. We can see you. Fantastic.
Okay, great. And so, yes, I want to share you some documents. I have prepared many of them. So I hope that I will be able to answer all your questions. So can you see my slides?
So we can't see them just yet, Lauren.
Okay, so I try a different
Fantastic,
command.
thank you.
Okay, is it better now?
Yes, fantastic. We've got it. Thank you.
Okay, so Yeah. So I'm here to introduce you OpenVIBE, and OpenVIBE is so I will prepare a different screen. Let me just few seconds. Yeah, because I have different materials. Yes. So now you should see in a large screen. Yeah, what I prepare to introduce you OpenVIBE. OpenVIBE is an open one software for brain-computer interface, but more generally to record and process in real time neuroscience data. And the interesting things with OpenVIBE is that you have different levels on interaction with this software. If you are expert or operators or just users, and so you can use it also for teaching or for your clinical process, as I am doing with it. And so you have this web page, openvibe.inaria.fr, that you join and see maybe details about this software. So in particular, you can process brain-computer interfaces with it. And as you can see, we have many applications with this software. Is one of the major used in BCI community. In fact, the short history about this process, you can see many funded projects that use OpenVIBE from now 15 years. It started with the French national project, and now it's extended to the wide world community. What I prepare to introduce you OpenVIBE is just a video. So I hope you can see it well also. So the most important thing is that it's open source and free software with a specific license that allow you to keep your code free and disponible for everybody. If you had something, this license contaminate your code, and so you keep it free. We have many platforms. You can see details on the web page. So mainly Linux and Windows, and different versions for Linux. And so the main thing is that you have many let's say modules that allow you to record first your data, especially from EEG devices. So you have two parts in this software. The first part is the acquisition server that you can manage. You have many also already headset in it, and you can just select which one you have and change some parameters such as the sampling rate and so on. And then so you can send this server, and we will collect data from the server using a second part of the software, which is a designer. And so I will introduce you just right now, which is the main part where you can design your processing chain using a lot of modules to filter, to classify, and to produce also a very interesting video output. So the main thing is that you have many boxes that you can arrange using our very efficient graphical interfaces. That's the most interesting part for me for this software, because it's not that common to be able to click and paste what you want to do in BCI. Especially, you have several libraries, and you have also other platform, but the strong features from the OpenVIBE is that you can interact with these graphical interfaces that we name the designer. And so you have you have a library, and with a lot of modules. I try to find the best way to show you that. Maybe just reducing. Okay, here, and you have also a search bar to select which process you want. So if you want to acquire the data, if you want to filter, if you want to select channels and rename channels and so on. So as you can see here, this is very, very short illustration. You have just two modules that you can connect one to the other, and finally interact with the acquisition server and visualize the data. So here it's just 3 random signals that you can visualize in real time. And so this is the main principles, and you can complexify the process with parallel lines and so on. So you have many plugins organized in different categories. For example, the first column is which kind of data you can process. So you can process online data, not only from EEG devices. You can also use, I don't know, ECG, EMG, whatever you want. If you have temporal data, you can have also markers, so triggers that you can add, and you can of course save them in different file formats, or GDF for general data files, that is an extension of the EDF format, European data file, to have many information in your data, and you can read them later for offline process. You have also several boxes for temporal analysis or for frequency analysis. I can give you details later. As you can see, we have also some boxes for pre-processing, and in the BCI community, we use, for example, two well-known pre-processing named XDONE, especially to highlight event-related potentials, or CSP for common spatial patterns that allow you also to highlight the variance of one class versus reducing the variance of another class. Is very useful when you try to detect mental tasks, especially motor imageries. And you can also create your own process. We have a DSP module, and you can write a mathematical formula to change the value of the signals. You can have autoregressive coefficient classification and so on, and you can visualize finally your signals or your process with 3D maps, for example. And another very interesting part, I think, with OpenVIBE is that you can interact with other softwares, for example, MATLAB, just using MATLAB script. And so we have an interface that is able to interact with MATLAB, Python, use LUA script, and also to have a very good interaction with virtual reality software using the VRPN protocol. So you have many modules that we call plugins, and you can of course add others concerning your own process. So a lot of them, all these plugins that I show you are already available. And so you can have many applications, and when you download OpenVIBE, you already have some very famous applications. So you can see, for example, a P300 speller to be able recognizing ERP, event-related potentials, to spell letter by letter what you want. It's a very well-known application for people with motor disability, especially locked-in syndrome patients. Or you have this GRASP protocol for motor imageries that you can also very easily use because it's already implemented. So you just have to read the scenario. A scenario is a processing chain, and people already propose many other applications. For example, this one is with steady state visually evoked potential. So you can use it for different kind of feedbacks. And so before to go forward, I just want to try to give you some details about how it's possible to do that. So it's mainly because so you have a kernel for this application, and it's certified. For example, if you want to develop some medical application that is certified, you already have this main part, the kernel, and the acquisition server that is already certified. So that doesn't, you need to certify your whole process, but this part is already prepared for that. And then you can add many plugins, and I introduced you some of them to interact with the subject and to present him different feedbacks. Okay, so the main part is just to select which process you want and connect them, the one to the other one. So for example, if I show you details about that, you can see here that you have a processing chain that you can select from the right side of the picture to have, for example, the acquisition, the filtering, channel selection, and the visualization of these signals. And so you have input and outputs for each modules, okay, each box. And you have to, according to, let's say, the specificity, the types of the input and output, you have colors, and then you need to connect inputs and outputs of the same colors. For each box, you can also change some parameters, and then you just need to collect them to have a more complex process. Okay. So I just introduce you briefly, yes, what is possible to do. You can also filter, for example, some channels or some frequency bands. So each box has its own parameters, and you can select them to visualize what you want. You can also design your own process or your own mathematical operations with this specific box named simple DSP to have more and more complex process, especially to be able, for example, to recognize one kind of event in your signals. So you can have special filters, and you can also select some specific frequency band and so on, and process parallel lines for different, for example, frequency bands. And so you can rearrange the outputs in different windows. So you can have, for example, an operator view and also a subject view. So that's very interesting if you want to control also the signal when you are recording them or recording them. And so we can also interact with the LUA simulator, and so to produce sounds, image, and so on. So you have many options to be able to use OpenVIBE. And so yes, that's the main process. So at the end, you can have your own chain, and for example, you can have one chain to record data, and if you want to try some different classification process, you can try them offline, and then select the best processing chain for your online acquisition. So let me know when I will have just 5 minutes more, because I can speak about OpenVIBE for many hours.
No, that's I can see why you're able to do that. Maybe if we go for 5 minutes more now.
Okay, great. Thank you.
Thanks.
Yes. So another very interesting part for me, it's because so it's a community. So I will go further just to show you, for example, more details about the acquisition servers. So you can use brand products, MOTV, GTech, Micromed, OpenEEG, and so on. So just go to the openvibe.inarea.fr webpage to have the full list because it's already updating. And so you have the main paradigms. So about ERP, event-related potentials, you can have SSVP, you can have motor imageries, or have proposed neurofeedbacks. You have many also outputs, visual output or auditory outputs and stimulus that you can propose to the users or to the operators, for example, to see details in frequency bands, so in 2D or 3D. You can have this, and it has already been used, for example, for education with children to show them, for example, when you move your right hand, which part of the brain is involved in this action. And so you can interact also with many different softwares and have different views. That's very useful. I already mentioned that, but I think it's something very, very pleasant with this software to have an operator's view, a subject's view, and also a designer view. Okay, so the last point I wanted to mention is the community, because now this 15 years software has a lot of users, and you can contribute to it. So using it first, so we can have feedbacks and know how to improve him, and so on the web page you can have the contact with the engineer that leads the project, and you can also create your own plugin, your own box, and propose it to the community. So just go to the web page. You have also a GitLab to have sources and try to improve it, and so we have everything useful for the community, such as a forum or a bug tracker and so on. So you can, of course, help the community, especially for now. We are trying to expand OpenVIBE to have more and more people involved in this project. And especially, I will just give you my last slide about this, about the future or what you can do. And for this, for example, so we are building, yes, a consortium. So to have, for example, a lot of engineers that are full-time on this software to answer your questions and improve or develop your needs. And so you can also go to the web page and see how you can participate to that if you have if you are a company working for an academy and so on. So it's also possible, yes, to join us, to join this OpenVIBE community and the OpenVIBE consortium to develop this software. I think my 5 minutes are almost done.
I think you might be right. Did you want a final sign-off?
Yes. So usually what I can do, it's, yes, to show you, for example, and discuss many applications that have been developed using OpenVIBE. And so you can see that, for example, you can also process data when two people are interacting using a brain-computer interfaces. So this one is, for example, for motor imageries. They are quite old now, but you can see the different paradigm. It was the first developed application 10 years ago. For example, this one is by Fabien Lotte, so one of our well-known researchers in the community. And you can have also application, especially, as I mentioned, interacting with virtual reality in 2D, 3D, immersive, non-immersive, and so on. And you can just develop your own application and your own needs. And you can also not work only with EEG, but I, for example, also work with spike trends. So directly the activity of neurons from the intracranial data. And so, for example, that's me controlling a robotic arm using combined motor imageries, for example. And so I can let it go if you have questions.
Fantastic. That's absolutely brilliant. Thank you so much, Laurent. Great to see you controlling that that robot arm. I think that's something that a lot of people on this call won't have had an opportunity, but I'm sure they would be really keen to do so. Brilliant. And thank you so much for your time. And thank you, Brian, as well, for posting a link to supported devices through OpenVIBE and also the community as well. I'm sure a lot of people here would want to join that community. So thank you, Laurent. Brilliant. So I think it might just be about time to hand over to Yuri Nusden from Resonance, who's joining us all the way from the Netherlands. Yuri, would you be happy to unmute yourself and share your screen?
Can you hear me now?
Yeah, we can hear you. Thanks, Yuri.
Okay, good. And maybe I'll start the video stream, and now I can share the screen. Oh, yeah. This is mine. Okay. Yeah, I'll start a little bit about myself because right now I'm in the Netherlands, but I moved here only 2 years ago. And before I worked in 2 Moscow laboratories, the Kurchatov Institute and Moscow State University, and I still have collaborations with them. And my job was to facilitate the creation of experiments, mostly as a software and a little bit as an electronics and mechanical engineer. And back in 2014, I guess, I started the BCI framework, which helped me to create these experiments, and I named it Resonance. And today, I want to maybe give you a little presentation, not about the resonance by itself, but of course I'll describe it a little bit in the end. But I also want to share my ideas why I started a new framework in the first place. And my main concern is automation of the experiments. Should we do it? How should we do it? Why should we do it? And I found several good reasons. The automated experiments, well, basically the experiments are overwhelming for the experimentator. And when you write a series of 3-4 experiments per day, so you are not only tired, you making mistakes, you start making a lot of mistakes, and you try to recover for these mistakes, you try to be faster, you try to shift times, and then you're nervous, and then it's basically a positive feedback loop, which leads you just to frustration. On the other hand, if you have the automated experiment, it not only makes you faster, you can delegate this work to somebody else from the laboratory, and you're not worried that well, the experiment is performed incorrectly, or you gave not a very correct explanations, or something like this. And the second benefit is you can also return to this experiment later. Like imagine you made the experiment, you write the paper, and a year later you have an idea, oh, I have a very good idea to continue this experiment, but now I need to restore everything. I need to find the descriptions, I need to find the procedures and instructions. This is maybe a problem for you. And if you have the automation, you just store it somewhere as a files on a disk, and then you can come back and start it again and run it again and again. Just a small example. Like imagine you have something very simple like a P300 experiment or something like this. And you want to control the impedance between the trials. So you write the trial, you check the impedance. How you do it? Yeah, you can take any existing software and it gives you a P300 experiment. And then you need to run the experiment, then you need to stop, you need to enable the impedance mode, you start the impedance reading, you are working with the acquisition software, you take a screenshot, so write down, you stop it, then you start the experiment again. And you do it again and again, but indeed, it is, in principle, it is possible that the computer does it for you. So you just press a button, and the experiment starts, the trial is ended, and it automatically switches to impedance recording and record the impedance while you give next instructions for the user, let's say. And what is the benefits? It is extra work to do. You need to code it or you need to find a way to do it. But in a series of the experiments, indeed, it will be faster. But not only. Like, imagine you registered impedance and later in analysis, you notice strange EEG in one channel and you wonder, well, what is it? You start looking at the impedance recordings and you see that the electrode sometimes disconnects while the subject is listening because he moves his head and then the connection is lost. You go, you check, and okay, basically the wire is dead. You don't need to guess. You don't need to come back to the experimental setup and check what's wrong with the setup. It's very easy to analyze the data when you have the data. And it's not the only one way of extending the experiment beyond the just running the trials. Because yeah, usually we describe the experiments like this. You have the acquisition, preprocessing, and classification, but it is not really how the experiment look like. It usually looks something like this, and it's an image from internet, but I really like it because you have a lot of things on the screen. You have the stimulus presentation. You have the screen for the experimentator. You have the device. You can control the acquisition device. You can control the computer. You can control basically everything you have connected for your experiment. You just need the tools, to do this, and to do this indeed effectively and not in a very hard way. I give you another example. This is the real experiment I created on the Resonance platform. And we wanted to record the EEG activity related to the transcranial magnetic stimulation of the motor cortex. So you have this coil which produces the strong magnetic field, and this actually triggers the region of brain. But we looked at the motor cortex and there was a problem. The participants, they should not tight their muscle. Otherwise, the recordings you make is blurred by their muscle activity. So what we did was set it up the EMG. So we're recording EEG and EMG in parallel, and we are processing EMG data in real time. And this controls this green bar on the right side of the stimuli. So if the green bar is green and below the threshold, this means that the muscle is relaxed and the experimentator can go. And he sees the screen and he triggers the stimulation. But there is another problem. What if he misses? Because this region is hard to catch. And probably he shifted the coil a little bit to the side, and then he stimulates completely different region. And you can process the EMG data again. You synchronize it with the simulation, and then you'll see these spikes. So this is the real life example. You'll see these spikes related to the stimulation of the brain, and you can immediately calculate. You can visualize it, of course. You visualize it only for the experimentator, and you also show the parameters like the millivolts, the latency. And this gives you all the hints you need to know if you stimulate the desired region, if you stimulate it with enough power, because there's a possibility to change the power, the amount of stimulation you apply. And this is a completely different experiment when you have the better control of the environment and better control of what you actually do. How to achieve this? Indeed, there is all the devices in your laboratory, you have access to them, but you need to control them. And it's a normal approach that basically Resonance provides the services. Every service is, you can think it like a acquisition device or the stimulation device or the program which controls the image on the screen to show for the participant or for the experimentator. And the different services have the configurations. So you understand the configurations, but they also have the internal state. The state machine controls the operation mode of the service, and they have input data streams. And all these three items, configuration, state machine, and the input data stream, you can control by other services. So instead of making adjustments in a UI or something, you can have the automation. Indeed, there is included the UI to make these adjustments during the experiment preparation, but the benefit is that it's programmably controllable if you want it. So you can write a program which switch the acquisition mode of the EEG device before the trials. You can control the power of stimulation for the TMS device. Any device you have, they have the options, they have the working modes, you can control them during the experiment. And indeed they send the data streams, and the data streams can be connected to each other, so you don't need to write the big application. You actually take these different services and combine them to have your experimental setup. And it's usually the service which controls the experiment. In terms, it's just steering it. It's like start the trial, start recording to the file. It's just coded inside to do this loop again and again. And then it changes the operation modes of the services. It reconnects it if it desired. And you have the models for the data processing, which process the data in runtime, indeed. And you have the feedback. So, and it's up to you how you connect them. It's could be very similar to what other frameworks provides. It's just a different approach. Instead of having the UIs or configuration files, it's available through the code. And when I talk available through the code, it could sound very scary, like you need to write a lot of code, you need to know C++ or something. And indeed, the thing is written on C++, but it actually has the QML interfaces for it. And the QML is a very powerful language for the user interfaces, but it actually just a JavaScript with some flavors. So the JavaScript is a very simple language. Everybody can understand it. There is a lot of tools. It's actually based on the very good, very mature framework Qt. And it provides you a lot of tools to develop this kind of applications. with the resonance library. When we talk about data processing, indeed, there should be a solution to do the runtime data processing as well. And in order to achieve that, there is separate framework for this. It's actually two of them, because one is written on Python, one is written on R. And both of them, the goal is, okay, we want to have this definition. There is only one human understandable definition of how we process the data, the blocks connected with arrows. But we want to have this in a controlled environment, so we can maybe reconnect them, maybe just change configuration as a reaction to the external events. And let's say you write it on Python, and that's it. It's a Python. If you know the Python, you can do this. The library is not very difficult. And in the end, you can have something like this. Like you can have very simple data flows on the left side, or very complicated data flows on the right side. And you actually can even ask the library to draw these diagrams, because it's automatically generated. The benefits of this approach, I understand that it is not doesn't sound like, yeah, I have the NumPy, which is data processing language or library, sorry. But this library is not focused on the data processing by itself. It's focused on building these pipelines and executing them efficiently online and offline. So you actually can have exactly the same code. You run it, let's say you create a new experiment, you want to try the new learning model or something like this. You start with the offline data, you start with the offline code, you create this Python code, let's say, and you test it. You're happy about it, you can plug it in an online environment without any change. And because of how this framework is organized, and because there is extensive testing of this framework components, you can be sure that the results you'll see in online experiments will be exactly the same as offline data modeling, which I found very important task. And yeah, in the past I struggled a lot with the discrepancy between online results and offline modeling, and that was a driving reasons. I want to write the code, I want to write the model offline without access to the devices, without making the experiments, but then I want to run exactly the same I modeled in my laptop. I don't have a lot of websites or something, but the main parts are shared in a GitHub, so you can access them there with the free licenses. This Python engine and R engine are GPL libraries, and in fact, if you want to have these abilities in other frameworks, the libraries are not tightened with the resonance, so you can integrate it in your software, or you can integrate it in existing software as well. Yeah, I think I have a little bit time for the questions now.
Oh, that's fantastic. Thank you so much, Yuri. That was really, really interesting to see. We've got a lot of things going on in the chat, asking for links and sharing those. So thank you for sharing those with us. It's fantastic. So what our agenda today was originally to have 3 speakers back to back and a global Q&A at the end. But I'm aware that Laurent has important things to do, and he does need to leave us at the end of the hour. So what we're going to do really quickly now is just have a couple of questions that have come through from our viewers for Laurent, just so we can make sure those get answered before he has to nip off. And then we'll have Robin's talk, and then we'll do a general Q&A for Yuri and Robin. So a couple of questions for Laurent, if you can hear us okay, and I might just unmute you in a moment so that you'll be able to hopefully answer these. First of all, we did have a quick question about whether OpenVIBE works with Mac that Laurent, I think you answered that one in the chat, just to say that it's not supported, but it sometimes happens. So if you're working on Mac and you want to try OpenVIBE, you can try your luck, but no promises. So 2 questions that we haven't answered yet for Laurent. So one is from Eric Lloyd through Zoom. So thank you very much for sharing that with us. We have a question: if you have a custom neural interface hardware, can you connect this to OpenVIBE as well? Laurent, what are your thoughts?
Which kind of, sorry, what you said? It's
so,
about which kind of device?
So I think it's if someone's working with custom neural interface hardware, so sort of not an established device.
Okay.
You don't have a kind of name, but sort of just generally custom hardware.
Yeah, so I've answered and give some answer in the question and answer sections. On OpenVIBE, you have one document and tutorial to build drivers for your own equipment, and especially for your own acquisition device. So you should find in this section, it's openvibe.nria.fr/documentation, and then looks for acquisition server, and you have a tutorial. If I can share my screen, I can show you, for example, these pages right now. So it's here, and you have several tutorials about how to build your own acquisition server. Yes, for your equipment. And as I already answered to another attendant, it's usually now OpenVIBE, it's quite well used, and so the manufacturers ask us how they can develop the drivers to have their equipment in OpenVIBE. So you can also try to contact them to push them to do it. But if you are your own equipment, yes, you can follow this tutorial.
Fantastic. That's fascinating. And I think that sounds like the answer that Eric Lloyd was looking for. Brilliant. So just one other question from Anshay Agwal. How does OpenVIBE sync the data between the stimulus, so the system presenting stimulus on a monitor, and the system recording the EEG during an experiment?
Yes. So there is, let's say you have different channels that you record, and one of them is for the triggers. And so for triggers, we are recording different types of triggers. So you have also one specification on the web page. It's named stimulations, and you can see that we have already different names for the stimulations, for one-node stimulation. So maybe I just need to look for stimulations and OpenVIBE, and you should find this specific line, sending data in OpenVIBE. So we record, yes, the type, we record the timing and the duration of this stimulation. And so we have also, we synchronize this event. You can do it also using hardware. So it's also possible, for example, to have a very good synchronization, because it's very important for some specific device, such as the event-related potential, to be very precise. If you are studying the, for example, the 200s or 400s or 170 component or the P300 component. So it's you need to have a very good timing, and the trigger should be very well aligned with the signals. So you can create your own stimulation with your own code, but you also already have I don't know, something like 40 names corresponding to triggers for when you start the experiment, when you start run, a try, when you send a specific motor imageries, and so on. So I can also answer in the question and answer section to where you can find this stimulation.
Fantastic. That's brilliant. Thank you so much, Lauren. We really, really appreciate your time. I'll let you hop off now, and we'll make sure to keep the discussion going afterwards. So a giant thank you from us. We really appreciate having you on this talk, and hopefully we'll see you at some of our future events. And for the moment, what I would like to do is now hand over to Robin Schurmeister, who is joining us all the way from Germany, from BrainDecode. Robin, would you be happy to pop off mute and to share your screen?
Yes, of course. Thank you very much. I will try to share my screen now. Let's see whether it works.
Yeah,
okay.
We've got you. Thanks, Robin.
Perfect. Okay. So yeah, I will talk today about BrainDecode, which is, as written here, a deep learning toolbox for decoding EEG. And it started out as a project here in the Neuromedical AI lab in Freiburg. But now in our new version, we have several contributors. So we try to make it more into a community project. So we still have us from Freiburg, but we also have people from the CEA Cleanatech and the University of Grenoble-Alpes, as well as people from INRIA Paris-Saclay. So also people who are involved in MNE are also now involved in the in this BrainDecode project. And yeah, so also just as information, for those that have used BrainDecode already, this is a new version. So we've kind of decided to rewrite it, make it more clean and nicer. And so in the email, for example, there was still like a link to the old version, but now every old version should clearly link back to this one, our new like braindecode.org version. And what I want to do today, I want to just show you like a tutorial what you can do with our framework if you want to decode some EEG. And you can follow along. It's a Google Collaboratory. So you can open this link. I will maybe just post it also again in the Slack here. Yeah, so the BrainDecode link, which was now posted in the Slack, as said, is like the old version, but there will be a link to the new one if you go to that. Yeah, so you can follow along in this tutorial. And in the start, of course, you would just install it through pip. So the new version is already on PyPy. And I have done that already, so I don't need to do that now. And here you can see like the first thing that we also supply in the new BrainDecode, which is like a more easy way to fetch some data sets by integration with the mother of all BCI benchmark project. So here, for example, we will now load the BCI competition 4 to 8 data sets. So it's like a data set of imagined movement of left hand, right hand, tongue, and feet. And yeah, this is just like a very easy way here now to load the data set. But if you have your own data, of course, you can load it through MNE or also NumPy. And we have tutorials how you can basically easily get your own data set into BrainDecode compatible format. And then, yeah, so what is this kind of data set? If you look inside, it will have a description basically showing you what kind of sessions there are. So there were in this setting six training sessions and 6 evaluation sessions. And inside the data set, this is a list, of course, of data sets. And each one is just the MNE raw epoch, sorry, an MNE raw object. So kind of what we wanted to do with the data sets is we didn't want to now, let's say, re-implement all the signal processing and all of that. So we just provide some SYN wrappers that give you some useful functionality, but everything should still, all the signal processing can be done through MNE or just through NumPy, as we'll see now. So now we'll have here some pre-processing. We want to do some bandpass filtering. And yeah, this one, you can see it here. We will do bandpass filtering between 4 Hertz and 38 Hertz. And there we just have a like MNE preproc wrapper. It will just call the MNE function. Here it will first just select EEG sensors in this line. Then we also can do like a NumPy pre-processing. In this case, you will just multiply the data by 1 million to go from volt, which is the default in MNE, to microvolt, which is much more appropriate for deep learning. Because in deep learning, I think one of the most important things that the stuff runs and your network can train is just that the data is in a reasonable range. And that's why we also kind of provide these tutorials so that you can get started more quickly and don't get like hung up on yeah, typical problems that you might encounter if you first start out with deep learning on EEG. And then here we do the bandpass filtering. As I said, this is also just calling an MNE function. So if you supply some string here, it will just kind of execute the corresponding MNE function. And you can also just supply the function itself if you have a function that works on MNE data. And finally, we had also like a new function in our framework, which we found very useful, often for EEG decoding, which just runs through the raw EEG recording, and does exponential moving standardization. And yeah, we just applied that so that you can also basically reproduce the results from our 2017 paper, which was the basis of the framework originally. So yeah, if we just, yeah, actually I can just run this now here, and then it will pre-process the data set in place. Actually, let me check. I can run the two things maybe, since otherwise I might pre-process it twice. So it's pre-processed already. Yeah, so you have some basic like pre-processing pipeline functionality, which just kind of calls MNE or NumPy function, so you don't have to learn anything new. And then now you want to, of course, cut some trials, or what we call cut compute windows. We will see why we make this distinction later on. And here, what you just have to specify is, for example, do you want to cut some part also before the original trial offset already, which we found sometimes helpful for decoding, that you have some baseline before inside for the network to see. Yeah, and we just yeah, compute this here into a number of samples and then do this cutting. And then you have a Windows data set. And this Windows data set is really like a collection of input windows that you can train the network on that are all the same size and so on. In this case, for trial-wise decoding, it's just the trials itself. And now, of course, what you want to do, you want to have some train set and some validation or test set. And therefore, we also provide some like splitting methods. As you saw before, this data set description, if we go back here, this data set description, it had stored like which session was from the training and which session was from the evaluation. And now we can say we want to split according to these sessions. So we have a training set and the evaluation or validation set. Yeah, and now, yeah, did that. And now finally we get to the deep learning part. So we want to create our models. And here one of the ideas of BrainDecode is to just give you some established models. So we have the ones from our paper, so deep 4net and shallow FVCSPnet, they're called inside here. And they're also EGNet from a different group, and we plan to add more and more models. And of course, if you want to contribute and add your own model, that would be great. It just has to be a PyTorch module, nothing special about it. Yeah, so here we would create this model. And now we'll go to the training. For the training of the network, we decided to use the Scorch framework to kind of make it easy for beginners to start it, because it has a very like simple API similar to scikit-learn. So it's basically like a scikit-learn PyTorch mix. And yeah, you can see here, you can supply some loss functions. This is just a standard loss function, negative log likelihood. You supply your optimizer and so on. You say, okay, my validation set is, yeah, I should want to evaluate on it. And then you have learning rate, weight decay. We supply also some default values here for our networks that we found to be helpful. But yeah, we always encourage you to do some cross-validation on your training set to find the ones that work best for your data set or for your task. We also tried to always in these tutorials to give you some reasonable defaults that should work very well in deep learning. So we also, for example, here use something that decays the learning rate over time, so so-called learning rate scheduler. This is cosine annealing learning rate scheduling, which has been shown to work very, very well, especially if we want to get fast results. So now if I run this, it will call this Scorch fitting function. And you can, like, while it's running, you can see here how the validation accuracy goes up and the training accuracy goes up. And you see this kind of typical but also desired behavior in deep learning, that for the training error, you will get close to 0. And you won't be as good on the validation set, but it will also improve. Yeah, and then you have basically already trained your first deep learning network on EEG data. And now you can also plot the results a little bit. So what we do here is we just take the Scorch history. So Scorch stores some history during the training, how the training accuracy was and the validation accuracy was in each epoch. And if you do that, and you can just plot it using your typical plotting functions. And yeah, you can see kind of how the training progressed from epoch to epoch, how the training misclassification rate went down, and alongside also the validation misclassification rate here, always shown the like red dashed line. Yeah, and basically just give you an idea what has happened and if everything looks fine. And yeah, so that's basically already all you need to just train your network. And another thing that you might want to do, of course, is you want to understand a little bit what your network might have learned or not learned. And one visualization we already supply here looks at how the amplitudes in different frequency bands affect your network after training. So what you can do is you can just look at for each class, if I change the amplitude in a certain frequency bin, how does my output of the network change? So you can imagine if I change the alpha frequencies on the left side, will it say it's the right hand or something like that? And we just have some function here that you can call directly and will do everything for you. You just have to give the data set, the model, and some batch size, and then it will compute you basically what I just said, how the a matrix which will tell you if I change a certain amplitude of a certain frequency, how does my output change for the different classes. And one plot I made here is just kind of showing you like a frequency spectrum, like you can see which frequencies the network even reacts to, and you can see, okay, basically above this frequency, it doesn't show any reaction, which is also expected because we did this bandpass filter around here, like 38 Hertz. And you can see that, in this alpha range, it seems to react, which is what you would expect as well. And that's why we look at this 7 to 13 Hertz alpha range a bit more deeply topographically. And if we do that, if we make this kind of plots, we can get some topographical plots. So we can see here, what we see here is blue means if I decrease the alpha frequency in this range, for my input, the network will give a higher probability for this class. So here we see on the right side, if the frequency decreases, the alpha frequency amplitudes decrease, then the left hand will be seen as more likely by the model, which is kind of plausible, with what you would expect from these motor imagery tasks. And one thing to note here is you need to be a bit careful about the interpretation. Again, you can kind of read a little bit about this in our 2017 human brain mapping paper on deep learning on EEG. There we explain a little bit like what you can see in these visualizations, what you can infer from them, and what you cannot infer from them. Yeah, so that's basically like a whole pipeline. And to finish up, I want to show like another way to train. This was now trial-wise training, so where you have a single trial, and then you have a single prediction, a single label, and you get your loss function and you train the network. But another thing you can do to be more data efficient is you could chop up your trials into many crops. So you could just take basically sub-windows of your trial and push them to the network independently so that your network has more training examples. This works especially well if you assume that you have some signal change which doesn't need the whole trial to be identified. So if for example, for motor imagery, you might expect these changes in the alpha range, and you don't need to look at the whole trial necessarily to identify it. And we provide some ways how to do that very efficiently. I'd encourage you to also, read a little bit more through the text that I have to go through very quickly now afterwards. Here we'll just do it. So what is different now from before is now you have to basically say how big should this compute window be. This is a kind of a computational parameter, basically some trade-off of how many of these, what I called here before, crops you process in parallel and how much GPU memory you need. And it just need to make sure that it's big enough so that your network has enough data to work on. And now if you do that, then you can create your model now. And now you have to also say basically how big do you want your model to be in the end? How much time should it see? And this is basically dependent on all the architectural parameters of your network, but especially also on how long is your final convolution of this convolutional network. And here we choose 2, and that will result in that case, for this network, in a net that sees about 2 seconds to make a single prediction. So let's run that. Then we have 2 helper functions, which will basically make sure that it really predicts every single crop it can. And that also ensures that now we know how to cut the windows such that from every trial, we really predict every single time step that's possible. Yeah, and that's what we'll do here. So now it gets a little bit more complicated, this cutting of the windows, because we have to tell it basically these windows inside the trial, how big they are and how much stride we want to have between them. Yeah, but when we do that, we kind of now also have this Windows data set, so a lot of windows from the original trials that we can now use to train our network. And if we do that, the splitting here is the same in training and evaluation. So if we now do it with the crop decoding, where we have more, as I said, more data points because we have these crops inside the trial, then yeah, what should happen now is that you basically see that this accuracy kind of grows a little bit more quickly than before. And you always see, of course, in the deep learning that these accuracies will not like monotonously increase, but they will be like changing a little bit back and forth. And you have to basically train it long enough to really see how good it can get. Yeah, and here I think I said to train for 40 epochs, so we have to wait a little bit, but we already see, okay, now it starts to really get reasonable validation accuracies. So here it's now above 70%, for example, and you can just kind of, yeah, see how it progresses. 75%, I don't know what we had before in the trial-wise. I think in the end we were a little bit lower. There was also a little bit less epochs, of course. Yeah, so here we were at like 61 validation accuracy, 61% validation accuracy after 20 epochs. Now we run it here for 40 with this cropped one. And after 21, we were, okay, we were at 70. Then again, since there is some variance, we dropped down. But basically at the end, we get much higher. We get even above 80% of this validation accuracy because we now use much more data. And that wouldn't go away if we also train the trial-wise longer. Yeah, so that's this crowd training, and then you can again do this same kind of visualization that we did before. Yeah, and then you will basically get kind of the same type of visualization and see the same results. And one thing which I wanted to highlight also is that we see some maybe undesired activity here, that the network also seems to react near the eye sensors a little bit, or near the like occipital region. And basically, this might be because we used also some period before the start of the trial where the people could see the things that they should do, whether they should move left hand, right hand, and so on. And if you redo this training, I will not run it now, but if you redo this training without this part, the accuracies are actually a little bit worse. Yeah, you don't get such high accuracies. But if you look at the visualizations, they look a little bit cleaner in that region, yeah, and they're a little bit more nicer that you just see this motor effect. Yeah, and you can see much more on the braindecode.org page where we have all the documentation. And yeah, we're always also interested in finding new contributors. So if you go to our GitHub, you can just create issues or contact us if you are interested in any kind of feature or you want to contribute something. Yeah, we're very open and welcoming towards any interested persons that want to use it. Yeah, I think that would be it for me. From me.
Fantastic. Yes. Thank you so much, Robin. That was absolutely fantastic. Thank you for a really deep dive as well. It's always nice to see those loss values ticking down. And thank you so much to Laurent, who I think is may have popped off already, and of course to Yuri as well. We do have some questions for you guys, luckily, and I'm pleased. I believe that Robin and Yuri will be happy to stay on for a little bit. So what we'll do is tackle as many questions as we can, and then if anything we're not able to get to in this time, we're definitely going to take those over to the Neuro bar. So let's see what we've got in the way of questions. So we actually have a couple of questions that are sort of specific for individual people, and we have some questions that are kind of general. So I'll sort of open those up to a chat between Robin and Yuri. But we do have a question for Robin really quickly. This is from Iya. Do you think the BrainDecode already has outperformed FBCSP and similar tools or not?
So I think it's a bit difficult to answer. Because, I mean, to be honest, probably you would need some kind of competition to answer it, because now we have a lot of data sets that people have already used for a long time and have kind of fine-tuned parameters for a long time. So even if you take these results, it's a bit unclear how much maybe this is just lucky overfitting, let's call it. Yeah, even if you didn't check the test set or whatever, even if you try to work very cleanly just by luck, you might have some unreasonably good results. So I think the first answer is we can't really know unless we kind of make some, let's say, new competition that really pits people that, let's say, are specialists in FBCSP and people who are specialists in deep learning to try out their best to decode some data set. Yeah, I think that would be my main answer. And second answer would be, I think the advantage of the networks is not even necessarily that they might outperform FBCSP in the domain that FBCSP was designed for. So let's say motor imagery or motor execution or any kind of oscillatory signals, but more that you can take the same network and apply it to very different tasks. So also some tasks like event-related decoding where FBCSP might not perform as good and get reasonable accuracies basically everywhere. So to have like a more versatile decoding tool. Yeah.
Amazing. No, fantastic answer. Thank you, Robin. I know it's a little bit of a tricky question. We do have a question that's come in specifically for Yuri, although I think this is potentially, in my opinion, one that could be answered both by both on behalf of Resonance and BrainDecode. The question is, how would you use Resonance and BrainDecode together?
It's actually an interesting question, and I saw a lot of offline modeling for in a BrainDecode, but in this presentation I don't see any online application of these models. But maybe Robin can answer if there's something for the online.
So we do also use it online. So we have a actually public framework, but let's say not mostly used internally framework to apply BrainDecode online. And there we also had the goal, similar to what Yuri said in his talk, that we have a guarantee that the same code is applied online and offline. So we also have something there. But since I'm not so familiar with Resonance, I don't know what would be the best way to integrate the two. I would have to get a bit more acquainted also with Resonance to see how they would be best integrated, let's say.
Fantastic. I think there's definitely an opportunity for a partnership there somewhere further down the line. Brilliant, fantastic. So we also have a question. What parameters should you consider if you want to implement BrainDecode in online prediction of motor imagery?
So I think if it's the question from the Q&A, they also asked about if it should be the same as a BCI competition dataset. In general, of course, what you always need to consider in terms of hyperparameters, I hope that's the question you have, it's like this learning rate, optimizer, and weight decay. And these kind of, you have to kind of, as I said, use your training data cross-validation to optimize them a little bit. And in terms of sensors or number of channels, as was asked there, of course, the way the network works now is if you train it on a specific cap, let's say with 22 sensors like BCI competition, then at the moment you can only use it if you have exactly the same cap again. So it wouldn't be possible to train it on a subset of sensors and then apply it to all or on different caps. We are kind of working on that because interesting topic and of course necessary. But for that, you'd have to, find some ways around this problem that at the moment it's designed for training on the same cap and evaluating on the same cap. Yeah.
Fantastic, that's great. I'm glad you touched on that. I didn't notice it was a two-part question that was also asking about, is it the same acquisition device and a number of channels? So thank you for answering that one. Brilliant. So we had a slightly more general question, which I'd love to get an answer from both of you, but I think I might start with Yuri if that's okay. This is from Elizabeth, who is watching on YouTube. Are there simple experiments that someone could do after obtaining a BCI system using your open source software? Like what's a good starting experiment?
If it's a question what is provided by the framework, right now, unfortunately, nothing. There is some examples on the web page, but there is no experiment like a predefined experiment. But if you really want to start, I can advise you doing something like P300 because it's really well described and it's not really hard to implement it.
Yeah, fantastic. I think that's great. I think the sort of oddball with P300 is always a great place to start. And Elizabeth, if you're still with us, I would recommend hopping into the Neurobar, join us on Slack, and you can see if you can discuss that with Yuri a little bit further. Robin, what do you think? What would be your first experiment to get started?
Yeah, totally agree. So actually my first experiment that I started with myself was also P300. Yeah, so I think P300 is kind of the easiest to set up also, and it's a very strong signal. So basically you should be able to decode it with a reasonable setup. So yeah, I agree with you guys there.
Fantastic. Brilliant. And another quick question for Robin. This is from Anirban, who I believe is watching on Zoom. So thank you for your question. Do you think the raw data should be passed directly to BrainDecode, or some kind of time frequency image could be more advantageous there?
So yeah, what we do is we pass the raw data. The idea for us was always that the network should be able to learn kind of if it needs to do some frequency decomposition, it should be able to learn that. So we always pass the raw data and have been quite successful and happy with that. Of course, you can try to pass a time frequency image, but yeah, for us, it's mostly been to the strategy to pass the raw data.
Fantastic. Great. And we also have a question from Mohit, who's watching on Zoom. Thank you for your question, Mohit. So how do you think deep learning will help in understanding the decoding? Since it's sort of a black box, how can you understand the mechanism behind the decoding? For example, the most prominent features or neural correlates? And that's
yeah, so about or okay. Yeah, so I think that this is a very interesting topic that I'm also at the moment, yeah, spending most of my research time on almost. So I showed some, let's say, semi-simple techniques right now, right, where you can see like how different frequency range amplitudes affect the network. But there is much more. Basically, you can mask out parts of the input and see how it affects the network to see if certain channels are even being used or not. And you can also start to investigate individual neurons. So we have a paper on like the hierarchical internal representations of deep networks trained on EEG. So there is already quite some research on that. And finally, what I'm at the moment also interested in is a subtopic called invertible neural networks. So networks that can be inverted, where you can go from the output back to the input. And these ones could also be interesting to investigate it more deeply. And I will give kind of a talk at the virtual OHBM this year about this kind of method. Yeah.
Amazing, fascinating. Yuri, what are your thoughts on that?
Yeah, to be honest, I'm not in the field of the deep learning, so it's a very promising field, and I'm collaborating in the experiments. I'm helping to prepare the experiments with the deep learning, but I'm not making the part of the learning by itself, so I cannot really comment.
Got it. I'll take that as watch this space. Fantastic. And Yuri, we had another question that came in for you, and I think it's maybe a good thing that we don't have Laurent on the call right now. How would you compare resonance with OpenVIBE?
It's a different software. So OpenVIBE is, if you want to take the P300 paradigm or something which is provided by OpenVIBE, and this is and you want to start, or this is enough for you, because there's a lot of different paradigms and a lot of different approaches to the experiment by design. And you can take OpenVIBE, you can take PCI 2000 or something like this. The tool I'm trying to make is focused on the automation of the experiments and the experiments which involves the multiple data sources. So something like EEG plus AMG, EEG plus eye tracking, or MAC data plus eye tracking. In that field, as I recall, OpenVIBE cannot provide you the full flexibility of what you can actually do.
Okay, fantastic. Thank you. Brilliant. And we have another question for Robin. And I realize just to our audience, thank you so much for sticking with us. I know it's really easy to sort of keep going with these questions. It's really fascinating content. We're going to see if we can wrap up in 5 minutes or so, but the conversation will be continuing in the Neurobar. So make sure that you are hopping in our Slack, hopping in that BCI 101 channel, and we will pop the link to the Neurobar there. And Robin and Yuri will be around to chat, as will more people from NeurotechX and from the community in general. So a question for Robin from Eduardo. Eduardo, thank you for your question. Thank you for joining us on Zoom. Could you give a very brief overview of your opinion of if and how general adversarial networks will really improve BCI classification?
Yeah, so actually we do have a paper on it. No. We do have one paper on EEG GAN on archive, and we're trying to update it and submit it. In this case, though, it was more about exploring and not necessarily using it to improve the decoding performance. I think in general, what we have seen from other fields is that you can use them to improve the performance, but maybe not much. I'm not very, let's say, I can't give very certain statement here, but it's yeah, certainly challenging also in the image computer vision community for deep learning. I haven't seen that the generative adversarial networks have been so, let's say, influential in improving classification accuracies or decoding accuracies. However, I think there could be some promise in areas where you have very low data, or maybe where you have more unlabeled data than labeled data. For example, one thing that where we have seen promise is that this is not EEG, but in MRI, where you may have a lot of recordings with some modalities missing. And there, if you have a generative adversarial network to basically infer the missing modality from the existing ones, which you can do even if you don't have any label for your specific task, then you can improve the performance. So it could be similar maybe for EEG with missing channels. When you sometimes have missing channels, you could train some GAN to, yeah, to reconstruct them, and in this way get more data to train your network. Yeah, that would be my answer.
Amazing, fantastic. So I think we might have time for one last question, and I think I'm going to have to be incredibly selfish and ask a question that is my question, hands up, but I don't think I could share without squeezing one in. So for a lot of the people in our community are, they're heavily involved in BCI, and also a lot of people in our community are really interested but haven't got started. And I'd love to hear from both Robin and Yuri what your thoughts are on this. Do you have advice for someone who's really interested in BCI, but they maybe don't feel really confident with computer software or with coding? If that was you, how would you get started, do you think? Should we start with Yuri?
This is a difficult question because I'm just trying to imagine myself. Okay, I'm just learned about the BCI. I want to start. I need an acquisition device. It's not a really easy topic to. Well, there's no cheap good ones, and this is kind of problem. So probably the best way to start with the BCI, and if it's if I understand correctly the question, because probably if it's a data scientist who just want to start with a plane with BCI data, there is a M&E and a lot of other data online already, so you can start. But if you are talking about the person who just learned there is a BCI and it will be really nice to try, unfortunately, the easiest way is to find a laboratory near you and join the experiments. Yeah.
Yeah,
OpenBCI, I see in the chat, OpenBCI is a really good hardware. I have one, but I can say it's really cheap if you're just interested in a BCI, and probably this is nothing for you. I cannot say you can just buy it to play for a weekend.
Amazing. Thank you, Yuri. And I think I actually agree with you. If anyone has a university nearby, assuming you're out of lockdown, they're always desperate for participants, and kind of being on the inside and seeing what it's like and making friends with people who are directly involved in that it's a great way to get started. And generally the neuroscience or the neurotech community, they tend to be really welcoming, and they're really happy to chat. Robin, what are your thoughts? What advice would you have for someone who's really interested in BCI, but maybe doesn't feel confident with the computing side of things?
Okay, so yeah, I think the best answer you both gave already is that, yeah, to find a team or to find other people who are already working inside and who can help you to get inside the topic, also help you to get inside the programming. Okay, I'm not sure because it's been a longer time, but since we also had presentation about OpenVIBE today, I would guess that actually OpenVIBE might be a good start because you can work graphically and kind of put the things together in a graphical way and get like a small experiment running immediately, or maybe even just kind of start with some pre-configured experiment. Yeah, so that could also be interesting start in that direction.
Yeah. Amazing. That's brilliant. Well, thank you both. So I think given that it's UK time 7:30 and we're about 30 minutes after our, I would say desired, but there are still a lot of people online. So I think the desired start time is maybe later than it would have been. We should probably take steps towards wrapping up. So I just want to say a massive thank you to Robin and to Yuri for their time and all of their insights and answering all of our questions, and a sort of a thank you to Laurent, even though he's not here, we'll certainly pass that on to him. And a thank you so much for everyone who's attended and contributed your questions. This event is part of a series. We're about halfway through now. We spent a lot of last week looking at the sort of consumer spectrum of BCI devices and learning about neuroscience. And we're going to have some more events next week as well. But I'd like to briefly introduce Brian Jenkins from NTX, and he is going to introduce our event tomorrow.
Excellent. Yes, thank you everybody for attending. Thanks to our guests and to the attendees for what was a riveting conversation, diving deep into kind of the tech opportunities for someone looking to get involved in BCI and some of the open source platforms available to them. There are a few things I want to just mention briefly at this point. We do have a workshop tomorrow, kind of building off of what you've learned today, where we can actually work through in an applied way and some of these programs so that you can become familiar with what it takes. So keep an eye out in your email inbox for that information. It'll be shared along with the registration link for tomorrow. That'll happen 1 hour at least before the workshop begins. And there'll be reminders going out later tonight, and that all this information is available on the event website. And we also do have an open social media contest. So if this is your cup of tea and you would like to win some NeurotechX swag, please post a photo of your setup, so how you are joining our webinar series, and make sure to tag NeurotechX, tag Skulltech, tag any of our partners, community supporters, etc., as well as your location, and let us know how you're joining, and we'd be happy to put you into a lottery for some free NeurotechX swag. That brings me as well to our Neuro Bar. So we've heard a lot about the Neuro Bar. It was a fantastic success last week, and so we are rolling it out again this week. It is tonight, 30 minutes after the call. We are going to share around a link in our BCI 101 channel on Slack for individuals to join, at which point the Neuro Bar will be open for all to attend. A drink is mandatory, so we ask that you bring water, tea, beer, vodka, whatever is your cup of tea, funnily enough, and join us for some amazing community conversations. Again, I'll also just remind everybody that the registration link for, the join link for the Zoom calls are shared at least 1 hour prior to the start of the call. So if you're looking to register to Eventbrite, or you having friends register on Eventbrite, just make sure that they're signed up the 1 hour beforehand, and they'll be included in the mass email that goes out. And we're also all available to help you if you do encounter any kind of technical issues. So reach out on Slack. Our emails are aplenty and available there, and we're happy to help. Thanks again to our guests, to our attendees, and everybody organizing, and we'll see you soon in the NeuroBar. I'll hand it over to you now, Sophie.
Fantastic. Yeah, a big thank you from me. So I think we'll wrap up the event as it is. Thank you everyone for attending. Thank you for our lovely speakers for all of your insights. Do get involved in NeurotechX. Follow us on, join us on Slack, sorry. Follow us on Twitter. You can find all of our details of different ways to get in contact with us. Drop us an email if you want to get really involved, and we'd be happy to chat. But in the meantime, thank you so much for your time, and we will look forward to seeing you in the NeuroBar.